So up until now, we've been taking a look at how to find limits, and the methods that we used were to use a table of values, as well as look at a graph to find the limit. In this video, we're going to take a look at when there is not a limit to the function. And there are three main types of scenarios where a limit just fails to exist. So let's dive in right now. So we have a function f of x is equal to the absolute value of x over x. Okay, and we want to find the limit as x approaches 0 for f of x. Alright, so we're just going to graph the function, and the graph looks like this. And we want to investigate the behavior at x equals 0. So we can see here that at 0, the value is undefined, but we can see that from the left it's approaching the value of -1, while from the right it's approaching the value of 1. So this is our first scenario where a limit does not exist. So type 1 is where the function approaches a different value from the left and the right, and therefore, because it approaches a different value from the left and the right, the limit does not exist. Because for a limit to be present, we have to approach the same value from the left and the right. So as x approaches c, from the left we're approaching the value of -1, but from the right we're approaching the value of 1, and because we're approaching from both sides at a different value from each side, the limit fails to exist. So this is going to be type number 1. And some examples where we can see this type of scenario is going to be functions like this absolute value function, as well as piecewise functions. And just to jog your memory, a piecewise function is where we have different domain values and different functions to represent those. So for example, we can have f of x is equal to the piecewise function, we can say x as x is less than or equal to 1, and then we can have x plus 2 as x is greater than 1. This would be an example of a piecewise function where we have different functions based on the domain value. So when the x is less than or equal to 1, well, the f of x is equal to x, but as x is greater than 1, f of x is equal to x plus 2. So we have different pieces that we kind of put together like a jigsaw puzzle, if you want to think of it that way, on the graph. Now looking at our second type where a limit fails to exist, this is the scenario where x increases without bound. Increases without bound. So what does that exactly mean? What does it mean to increase without bound? So to see that, we'll graph the function f of x is equal to 1 over x to the 4th, and we want to find the limit as x approaches 0 for f of x. Okay, so now graphing the function, it would look somewhat similar to this. We're going to have a couple of asymptotes as we graph this function, and our first asymptote is going to be at x equals 0, and another asymptote at y, use a different color, at y equals 0, we're going to have an asymptote. So what it means to increase without bound is basically we're approaching infinity. So if you look at the limit x as x approaches 0. We see from the left we keep going higher and higher and higher, closer and closer to 0, but we don't quite hit 0, because if we plugged in 0, use direct substitution, we would get 1 over 0, which is undefined. So because of that, basically we'll be approaching infinity from both sides, and x just keeps on increasing and increasing without a limit. So because of that, there is no limit, because we're increasing and increasing without a limit. We'll keep going to infinity. So that's going to be our second example. So again, the limit does not exist. So finally, looking at our third, this is somewhat uncommon. We don't encounter this too often. This is type number 3, where the value for x oscillates between two fixed values. And to look at this, we will look at the function f of x is equal to 1 over cosine of 1 over x, and we want to find the limit as x approaches 0 for f of x. So now, sketching the graph of this function, it's going to look somewhat similar to this. It's kind of an interesting graph if you graph it on your calculator. We basically just have it like this. And the reason is, if you graph this on your calculator, it's basically infinite jumps between these 2 points. And if we make a table, we pick certain values. We have f of x. We pick 4 over pi. We pick 4 over 5 pi, 4 over 9 pi, 4 over 13 pi, 4 over 17 pi, and 4 over 21 pi. We basically see 2 values that just keep repeating over and over and over again. That value is going to be 0.707, negative 0.707, 0.707, negative 0.707, and the trend basically just keeps on continuing. And the reason for that is because in this region, we're within the unit circle. So if we put in a small value, such as, let's say, 1/2, that's going to be cosine of 2. And if we put in smaller and smaller values, the value, the actual value, because we're doing 1 over x, the value is going to be the reciprocal. So the smaller the value gets, it's actually bigger and bigger and bigger. And if you get bigger and bigger and bigger, we just keep going around and around the unit circle. So we just keep hitting the values over and over again, no matter how big or small in this case, no matter how small x gets, no matter how big the value that we're taking the cosine gets, we just keep going around and around and around and around in the unit circle, like we are trapped within the unit circle. And because of that, we are going to see this oscillation between 2 points on this graph. And because because the value keeps oscillating between these 2 points, the limit essentially does not exist. And we really only observe this trend within the trig functions, where we have the unit circle. And these are going to be the 3 types of scenarios where a limit just fails to exist.